So, welcome back. After what I have done in the last lecture, today I take up a principle that was taught to us in the early classes, class 6, 7th, etc. And that was about lever. The lever, which is the principle of the physical balance also, what is called mizan in Arabic, is ideally we talk about a light rod. AB is a light rod of negligible, negligible mass pivoted at a point called fulcrum. This is the fulcrum. This is the point O will take here, and this we'll call the fulcrum. This can be situated anywhere on the line joining the two ends of the light rod. This is like what you have in children playgrounds, what is called seesaw. Okay, seesaw. Kids like to use the seesaw to play with each other. Okay, and this system I have shown here to comprise of a length AB, which I can say is equal to D1 plus D2, as has been shown over here. Okay, and I have a couple of forces acting at the ends, the force F1 and the force F2. Look here, these two forces are, both of them are vertically downwards in this particular situation, and therefore the translational equilibrium does not exist because the total force, but if we look only at these two. But there at the fulcrum there is a reaction, and this reaction force I have shown as equal to R. If we take all these forces into account, then even translational equilibrium exists, okay, along with the rotational equilibrium. Lever is a system of mechanical equilibrium. Mechanical equilibrium which comprises both the equilibria, the translatory equilibrium and the rotational equilibrium. So let us now look at it, and we take the origin, the fulcrum point. I can also call it fulcrum F, so this is F and O are the same point about which the things are happening. The rod is very light, and under that consideration we write the equation R in the upward direction, which is anti-parallel to F1 and F2, and so these forces R minus F1 minus F2 I write equal to 0 for the translational equilibrium, and for the rotational equilibrium I just write because the R is lying in the same line, so therefore there is nothing for it because its distance from the fulcrum is equal to 0. So what I get here is D1 into F1, which goes like this in this sense, and D2 into F2, which goes in the opposite sense. If the sense is anti-clockwise, like here, then that we consider as positive, and if the sense of the torque which develops is clockwise, then we call it negative. So with that in mind, I write f d1 f1 minus d2 f2 is equal to 0 for rotational equilibrium. And so from this equation I get this equation, d1 f1 is equal to d2 f2. It's a very simple equation that was taught to us in class 6, 7, one of those, and this was called the principle of moments, and some of the teachers and some of the books at that time used to write it as law of moments. Okay. And there used to be several questions regarding the balance, how to deal with the balance equations, whether the what is being weighed is correct or not. Okay. So D1 is the load arm. D1 here, there is a load, and this load is F1, and therefore we call it, this left hand side of the equation I call it inwards, that load R into load, okay, is equal to effort R into effort V2. Okay. So now we define something called mechanical advantage. Mechanical advantage is defined as this measure of this force, magnitude of this force divided by the magnitude of the effort. Okay. So it is the load divided by the effort. And it turns out readily from here that this is equal to D2 into divided by D1. If D2 is greater than D1, then of course there is an advantage more than one, and that is what is desired. Here, in this case, I have shown that the force which is acting for here is just perpendicular to the arm D1, and this force is also perpendicular in downward direction again, and there is an angle of 90 degrees. I am going to show to you in the next picture that even if these loads and efforts, they are making an angle with the vertical, even then this is going to hold. So this equation I am just going to show, this principle I am going to show in the next diagram, that we have it holds the principle of moments even if these forces are like this, okay, but they have to be parallel to each other. Okay.
Yes.
So as I told you, if I make a distinction that the load makes a direction theta 1, an angle theta 1 with the vertical axis, and the effort F2 makes an angle of theta 2 with, so why is it like that? Now all that we have to do is we have to apply the same set of equations, and now what we have to do is I will resolve this F1 into two parts, one along the vertical line, which is F1 cos of theta 1, and then I have this, when I resolve this, then I have F2 cos of theta 2, okay, and along the line joining the 2 points A and B, I have the resolved parts as F1 sine of theta 1 and F2 sine of theta 2. So what basically should be there, that F1 sine of theta 1 should be equal to, being opposite and cancel out, F2 sine of theta 2. So the effort has to be such that the theta 2 etc. will be determined by this, and I can write, if this is this, then sine of theta 2 becomes equal to F1 upon F2, which is the mechanical advantage, multiplied by sine of theta 1. So I can determine that the theta 2 will be equal to the sine inverse or arc sine of this F1 upon F2, the mechanical advantage, multiplied by sine of theta 1. This kind of relation has to hold, and this is how we can determine the angle at which the effort should be applied. And this is and of course, once this force, the dissolved component, cancels this dissolved component, then we are left with now a new force, F1 cos of theta 1 here. So I can write F1 cos of theta 1 into D1 into F1 cos of theta 1 should be equal to D2 into F2 D1 into F1 and D2 into F2 cos of theta 2. So this is how the principle of moments works, and the mechanical advantage in that case will become equal to F1 cos of theta 1 divided by F2 cos of theta 2. Okay, but that will remain equal to D2 upon D1. So with that, we close this principle of moments and rather take up a description of center of gravity and how it is obtained, how it is explained, and how it is related to center of mass. It should be always close to the center of mass, and at times coincide with the center of mass of the system which we have calculated before. So the item that I am going to discuss with you, to share with you, is what is known as center of gravity, briefly called CG. Okay. Here, what I do is, I take a cardboard of any size, etc. And what I can do about this cardboard, that by trial and error, I can balance it even at the tip of a pencil, which I have shown over here. So there are two faces. One face is up and the other face is down. Both of them are planar. Okay, so this is a laminar structure, and the surface vector for this is out of this surface, and the surface vector over here is out of this surface. Normal in both the cases. That is what has been shown. So if I take that laminar cardboard and if I balance it, okay, then I find that the total force acting in the system in the case of balance must be equal to 0. And there are, because the total mass is capital M, the force or weight associated with it will be equal to mg, and there will of course be a reaction in the upward direction of the cardboard, which is being balanced on the tip of the pencil, and this I am showing like R. So for the translational equilibrium, we have two forces which are acting in the same line, of course equal and opposite to each other, and therefore what I get is R minus mg is equal to 0, and therefore for translational equilibrium I have a simple relation that my reaction must be equal to mg. Remember, they are not the action-reaction pair, because action-reaction pair, they act on different bodies. And right now, in this case, this force is acting in the same body as this force. Okay, so bear in mind that. Now, the point at which the balance has occurred, okay, of a body which is constituted by many masses which are distributed over the laminar cardboard, and we consider that the laminar cardboard is of the same thickness and is made of the same material, so it is homogeneous, and homogeneous means it has got the same density everywhere. Okay, so if there is m1, then there will be a force in the downward direction, m1g, and if m2, then m2g, m3, then m3g, mi, then mig. This is what the various particles or masses which constitute the lamina here is made up of. Now, G is the center of gravity about which the torques are taken. If we take the torques, then I find that the sum of all the torques is equal to 0, because Fi is equal to mi into G. Okay, for any force that is applying on any mass I due to the gravitational field G, it turns out to be like that. Or I can write that the torque gravitation, okay, this is equal to sigma torque I, all torques put together. There is a body here, so if I take the torque, then this m1g into this distance from here to here, this will be m2g, and distance from there to there. That is how we are going to calculate the torques. And therefore, since this is equal to 0, and of course G is a constant, so what is left is sigma mi into Ri, or Ri into mi. But I have taken it as mi Ri because I have already defined the case of the calculations regarding the center of mass, that this is given as mi Ri. So the same relationship I obtain, that sigma of mi Ri is equal to 0, because the total gravitational torque on the system is equal to 0 about the center of gravity. So we conclude that the center of mass of the system is the same as the center of gravity of the system, capital G. Now this is normally true for small bodies of near the surface of the earth or otherwise, wherever the value of G, the acceleration due to gravity, what we call, or the gravitational field is constant and is the same all over all the points that we have on the defined body. But for large extended bodies like the Himalayas or the Alps, the center of gravity and the center of mass may not coincide. And it is true because G may not be the same all over. G may not be same all over because G depends on the height from the surface of the earth. G depends upon the location of the point, on the longitude, on the latitude that comprises it, etc. So in that case, for very huge bodies, very extended bodies, the center of gravity will be different from the center of mass, but for the smaller bodies, the center of gravity and the center of mass do coincide at the same point. And now I take up a couple of examples, okay, to calculate the torques, etc., and to learn how the balance is brought about. So I take up a otherwise simple problem, and I describe the problem like I said we should describe the problem in our own words. We have a beam of length AB, and this time I am not going to take beam as massless, but rather the beam has a mass which is described by W is equal to mg. I'm sorry, not the mass but the weight associated with this. And this is the center of gravity, capital G, which lies in between the 2 points A and B, which comprise the beam. I have two knife edges at the same distance A from this end, that is A to K1 and K to B, both are equal to A. So I take the length, the total length of the rod or the beam as equal to 2L, that is L plus L is equal to 2L. From A to G it is L, from G to B equal to L. Now I have a system in which there is a mass m1 which is separated from the G by a distance x. I can have this positioned on the left hand side of G, on the right hand side of G, at any distance away from G, it doesn't matter. So I have a weight W1 which is equal to M1 into G. Okay. Now with that, we have a balance. We have an equilibrium. What kind of an equilibrium? It is dual equilibrium, the translational equilibrium as well as rotational equilibrium. So what we do for translational equilibrium, you can see that there are two masses, two weights or two forces in the downward direction and two forces which are acting at the knife edges, which are acting as dual points on the beam, two knife edges. So let us see how we are going to proceed. Normally, in a question that we are asked, we are given these values in some numbers, but as per the instructions, desires of one of the Russians I keep in high esteem. What is the name of that? Anyway, so I am writing those numbers in symbols, okay, and solving the problem for us. So for the translational equilibrium TE, I have R1 plus R2 minus W1 minus W is equal to 0. Call this equation number 1. For the rotational equilibrium about G, we are taking the rotational equilibrium about the center of gravity of the system. However, it's not an essential thing. I can take it about any point. All other points are equally preferred. But while solving the problem, our instinct says that we should go for least action. And taking it at the point G makes the mathematics that will follow a bit easier. Okay. So for rotational equilibrium about the point G, it could be taken about the point P also, no problem. Okay. About the point A also, B also, this point here, point located at K1 and K2, anywhere. So what I write then is, now the sense is, for R1 the sense is like this, it is clockwise. For R2 it is like this, it is anti-clockwise. This has been shown over here for the solution after we make this sketch diagram. Okay, then R1 into K1G, R1 into K1G, this distance, plus W1 into PG, which will turn out to be X as has been indicated there, plus R2 into K2G, R2 into K2G. These two are positive, the first one is negative. Okay, so call this equation number 2. Now from equation number 1 I can write the value of R1 plus R2, which is W1 plus W, and from equation 2 by rearranging terms I can write R2 minus R1, R2 minus R2. Okay, this turns out to be equal to W1 into PG from here to here, which is X, divided by K1G plus K2G and K1G plus K2G. From here to here, this becomes equal to 2L minus 2A. So I get a result here for R1 plus R2 and R1 minus R2. These are two equations. If I add them, R1 will cancel out. I will get a value for 2R2, etc. And if I subtract this, from this, then what I get? Okay, I get 2R, and the results like that. And if we solve them, we just obtain the results like this over here. And of course, there is a subtle difference, a small difference, and I don't ask you to remember this formula. Please, for God's sake, don't remember this formula to apply it. What is the distinction that we must be able to observe? The distinction is that in the same thing there is a negative sign in the case of R1 and there is a positive sign in the case of R2. So this is how we can calculate R1 and R2 for the given set of data that we have, and the solution will be easier for you to obtain. Now I take another example from statics and solve a problem of a ladder which is against a frictionless surface, the wall, and of course there is a friction in this direction. And what is the condition? The ladder is not going to slip, etc. in the next problem. So, as I told you, I have a ladder and that is resting on a frictionless wall. But it can't unless we have a floor with friction, a frictional there is a friction on this floor. So when the wall is frictionless, and now the center of gravity of this ladder of length L will be midway at the point T. Okay, the center of gravity of the system, even the center of mass of the system can be like that. Okay. Now, let us say that this end of the ladder lies at a distance of x from the wall. Okay. And when we build up, we calculate this height from the floor to the wall, because this is L and this is X. So using the Pythagoras theorem, I can calculate the height to be equal to under root of L square minus X square. There is no problem in that. So we are asked to calculate F1, F2. Also we can calculate the normal reaction which is there, okay, and the value of the angle beta which the net force here makes with the horizontal axis. You can see that the angle beta is between F2 and this. Okay. So the force which is acting over here, this comprises of two forces. One is F and the other is the normal force that exists over here. Normal reaction of the flow on the tip of this what do you call it, the ladder. Okay. So we start, and we first of all calculate that F2, this F2 will be equal to this force from here to here plus this force which is normal reaction. So I get F2 is equal to F plus Fn. Okay. Now this F prevents the ladder from slipping. Okay. And now I write the equation for this is the habit that we must make. First of all, we should talk about the translational equilibrium. There is no translation, there is balancing, and there is a case of total equilibrium. Okay. So for the translational equilibrium, I can write how many forces are there. One is the normal force over here, and the other is the W, which is for the weight of the ladder, which is not 0. Okay. So it is finite. So I can write N minus W is equal to 0 is equation number 1. And then we talk of the forces in the horizontal direction. The forces in the horizontal direction are two. One is this force F, which is providing the friction force, and the other is the reaction of this wall to the ladder over there in the horizontal direction. It's not horizontal direction, it's the direction normal to the reacting surface. Okay. So I can write therefore for forces in the horizontal direction, because I said that if some kind of an equilibrium is going to exist, then forces in all directions should be can be considered, and we are considering the forces in the horizontal direction. Okay, and I get an equation number 2, F minus 1 is equal to 0. For rotational equilibrium, we take moments about A. We take moments about this point A here, okay, where it is, this is the point A. Okay, I can take about any other point of the system, but just for the sake of from experience, we choose the point for which the calculations have to be, our actions have to be least. So for this rotational equilibrium, we have to take the moments, and the moments are taken about A. In this case, I can see that there is one for F1 and F1 is away from this by the height, which is taken as L square minus x square under root, this multiplied by F1, and the second one is x by 2. Why x by 2? Because from here to here it is x, so this is x by 2 and this is also x by 2. We are taking about a, and therefore the distance of this w is x by 2. So I write this equation and I obtain an equation 3. Okay. So now look here. After I have done this, I am not taking any numerical values. You can be given numerical values. So I can get from equation number 1 the value of n is equal to w. The value of the normal reaction over here got to be equal to the weight of the ladder. From equation number 3, that we have over here, I can calculate the value of F1, okay, which turns out to be equal to this x2 upon 2 and this and that and into w. Oh, what a silly mistake I had made. Left hand side is force and the right hand side is just a mere number. So these silly mistakes happen. These silly mistakes happened with Newton too, and that is why he found difficulty in using the third law. I have not done it deliberately. Okay. From equation number 2, here, okay, I can write F1 equal to F, so the same result I obtain for F also. Now, F2. F2 is square. This comprises of two forces, F and N, so I can calculate it as root over F square plus N square. Okay. And we can see that the tangent of beta, this angle that this force F2 makes with the horizontal axis, tangent of beta is equal to N divided by F. Very simple. And when I calculate, I find the value of tan beta is equal to 2 under root of L square upon x square minus 1. Now, it is just coming to my mind that what will happen if x were equal to L. That is, the ladder were lying on the floor. Then naturally you can see that L square upon x square becomes equal to 1. So this is equal to 0. So tan of beta becomes equal to 0. Okay. Also the normal, if tan of beta becomes equal to 0, what it means? Either this becomes equal to 0 or this becomes equal to infinity, which is not a possibility. Okay. So tan beta is equal to n and n also becomes equal to 0. So these are some of the things which we can do if we describe the things with symbols. Normally, in a situation like that, we tell you the length of the ladder, say 5 meters, the value of x 1 meter, the weight of the maybe 10 or 20 kilograms, like that, and we ask you to calculate the value of beta, which is tan inverse of this quantity. Okay. So I have enjoyed doing this for you and hope that you also enjoy, and we'll talk about other nuances like the moment of inertia, which is a very interesting topic, which comes up in the next lecture. Thank you very much.